I will start recording now, Aris.
Aris, excuse me. How should I pronounce your family name?
My family name is Karasturgiu.
Okay, good. Thanks.
So, good morning, everybody. Welcome again for this new colloquium here at the Instituto Astrofísica de Andalucía in Granada, in Spain. And today we will have the talk by Dr. Aris Karasturgiu from the University of Oxford. And he will talk about pulsar astrophysics in the era of large surveys. So today is May the 4th with you, Aris. Isabel, please.
Okay. So good morning, everybody. Thank you very much for attending this new Severo Ochoa web colloquium. This time we don't have the pleasure to have the speaker in person, but it's a pleasure to have him online. Thank you very much, Aris, for having accepted our invitation. Dr. Aris Karasturgiu is an associate professor and senior research fellow at St. Edmund Hall in the Department of Physics in the University of Oxford since 2007. He graduated from the University of Bonn in 2002 with his PhD research conducted at the Max Planck Institute for Radio Astronomy. He got then postdocs at the University of Sydney and also as a Marie Curie Fellow at IRAM in Grenoble, and before going to Oxford, where he teaches special and general relativity for St. Edmund Hall. Dr. Karasturgiu is also a square kilometer array visiting professor at Rhodes University in South Africa. His main research interests involved understanding the pulsar population and astrophysical problems related to pulsars. He works on observational and computational techniques to achieve pulsar science goals with next generation telescopes, such as, for instance, the Square Kilometer Array Observatory, SKAO. In preparation for these, Aris uses data from telescopes such as MERCAT and LOFA and co-leads the 1000 Pulsar Array project on MERCAT. He's the PI of the group developing the pulsar and fast transient search component of the SKAO and is a co-chair of the SKAO Pulsar Science Working Group. And as René told us today, he's talking about pulsar astrophysics in the area of large surveys. So thanks again, Aris, and the floor is yours.
Thanks very much, Isabel. It's a pleasure to give this talk. I'll try to describe some key goals and key difficulties in pulsar astrophysics in this talk, and I'll intentionally describe some phenomenology that you may not often hear about in talks that address pulsar timing and pulsar searches. This is done on purpose to sort of give you another angle about why we're interested in studying pulsars the way we do. And I've tried to put together an informative talk with some sort of coherent narrative, but there are many aspects of this that I am not going to be covering today, which are, of course, equally interesting and sometimes quite enigmatic. And maybe we'll leave those for the next opportunity. So, well, from my point of view, we are conducting pulsar surveys to understand the population of neutron stars primarily, and then to use neutron stars as physical tools in experiments where they have a very special role to play. So what are the questions that we want to understand in terms of understanding the population? Well, we want to understand some very basic things, despite the fact that almost 60 years have gone by since the discovery of pulsars. We don't know how many there are, how many neutron stars there are in the galaxy, and how many of those are radio pulsars, and how many we should expect to see from those. And if we understood that, do those numbers agree with the predicted numbers and rates from various formation channels of stellar evolution? Once we have an understanding of this population, do we expect that different subgroups in this population evolve into each other, or should we understand this population as different subgroups originating from different progenitors or through different mechanisms. Radio emission in pulsars comes from the magnetosphere around the pulsar, so we still don't understand what exactly the radio emission process is, and that clearly is an issue because it's one of the main carriers of information to learn all of this stuff that I'm going to talk about today. We want to understand neutron star interiors and how they interact with the magnetosphere. And the reason I'm phrasing this question in this way, you may have heard before that people are interested in neutron star interiors, but my interest is more about how the interior interacts with the magnetosphere, in the sense that all the information that we're getting from radio pulsars comes from the magnetosphere, and we're trying to learn about the interior. So we need to understand that connection as well, better than we do today. Do we understand the magnetic fields of neutron stars? I would say we do to 0th order or to 1st order, but is that sufficient to be able to say that we understand neutron stars completely and to use them for the very careful experiments that we want to use them as tools for? And also, what are the actual limitations of using radio observations for exploiting pulsars? It's good to understand what we can and what we cannot do. The pictures I've put on the left of this slide, I'll come to during the talk. So the second reason we're conducting surveys for finding pulsars or studying pulsars is to improve the use of pulsars as tools for other experiments. So, for example, you don't necessarily need to know everything about how pulsars work in order to conduct high-precision pulsar timing experiments and to address questions in fundamental physics. And that you do by finding relativistic binaries or pulsar black hole binaries, triple systems that I'll talk about later in this talk. But there you can just assume that a pulsar or a given pulsar is just a clock, and you don't care about what it's made of or how it functions. You can use these sorts of pulsar timing experiments to work out neutron star masses from radio observation. And you can use, again, with respect to interiors, you can use pulsars as labs to understand the equation of state of dense cold nuclear matter. So the state of matter in the interiors of neutron stars is not accessible to us in a lab. So the pulsars are the only domain in the universe that we have to probe dense cold nuclear matter. We can use pulsars as gravitational wave detectors, and in some cases, pulsars as gravitational wave emitters as well. And this field is definitely gathering pace and has been over the last few years. And we can use pulsars to understand the magnetic fields in our galaxy at multiple scales using Faraday rotation measurements and so on. And there's lots of other interesting experiments that mainly come from the key property of pulsars, that they are very small, so they are kind of ideal point sources, and they have these extreme rotational properties, extreme rotational stability, and so on. So I think it's important to understand, and especially for people who don't think about pulsars every day like I do, what the actual observables are and which parameters are observed and which parameters are derived and which parameters are model dependent. I think that's a crucial thing to think about. And so this slide addresses this point. And so on the left here, I hope you can see the little red pointer there. On the left here is a typical figure of the pulse profile of a radio pulsar. This one's called J0738-4042. And what you see here is total intensity in black versus rotational phase. So the neutron star is rotating around its rotation axis. There's a radio beam. The beam is sweeping past the telescope. This is the phase of rotation on the x-axis, and this is the intensity. So what we observe, the observable, is the pulse profile, actually in full polarization. So you see in red here is the linearly polarized component, and in blue, the circularly polarized component. This panel above shows the angle of the polarization of the linearly polarized component, which you see is measured very well because the linear polarization is very strong. What else do we observe? We observe our instruments are typically broadband, so we observe this profile across a broad bandwidth. So this is, if I'm not mistaken, the bandwidth of the 21 centimeter receiver Meerkat. And so you see the pulse profile at the highest part of the band and the pulse profile at the lowest part of the band. This is just total power encoded in some color scheme. And we can also observe individual pulses. So this is a stack of individual pulses versus time versus rotational phase. And you can see the variability in the individual pulses from this source, which is typical of pulsars. So you can measure, what you can measure is the periodicity of the pulsar plus the periodicities and modulation times in the single pulses. So in terms of observables, the period of rotation is something that you can directly measure. The derivatives, the first derivative is the most important one, but also the second, as I'm going to talk about later. So the temporal derivatives of the rotational period are directly observable things. You can also make an image. In fact, with most modern telescopes, you have an imaging capability that exists at the same time as measuring things in the time domain. So the image gives you environmental data, so things to do with the environment of the pulsar. And from these parameters, you can also derive, to some extent, the interstellar dispersion. So the dispersion caused at radio frequencies due to the free electron content in our galaxy. Scattering and scintillation, which are, again, ISM-related phenomena that stem from anisotropic distributions of free electrons in the galaxy. Absorption by clouds of gas on the line of sight. And then you can also derive from these measurements accurate estimates of the position, proper motion, and to some extent the distance of the pulsar. And the reason I'm saying you derive the position and the proper motion is because these these fall out of the timing modeling. So if you have assumed that a pulsar is at a particular location and it's actually, there's an error in that position, that appears as a residual in the pulsar timing. So this is a synopsis of all the observable quantities. In the radio, pulsars are extremely variable. They're generators of fascinating data sets, time series, I should say. There's variability on all time scales and a complexity of phenomena that are both organized and stochastic to some extent. So this is a plot that I really like from a paper by Tim Hankins in 2003 that shows data from a purpose-built instrument that could record at extremely fast rates. So you see the axis here is microseconds, and these are microbursts, let's say radio microbursts from the Crab pulsar, which, if you look on the y-axis here, you see have a flux density that exceeds mega Jansky. For those of you who are not thinking about radio astronomy all the time, a Jansky is the typical sort of radio astronomy unit, right? It's 10 to the minus 26 watts per square meter per hertz. So it's a very, very small amount of power, but pulsars are typically micro Janskys to Janskys in their own flux density. So these observations that show that pulsar emission on the shortest timescale is extremely bursty and extremely bright quite revealing about the pulsar mechanism. So there's other ways to interrogate the emission mechanism. For example, the variability, the pulse-to-pulse variability. What does it mean in terms of the distribution of energy per pulse? So this plot here shows 6 histograms of the pulse energy for 6 different sources. And the interesting thing here is that the shape of this histogram is not always the same. So the emission mechanism can generate distributions of pulse energies that look like power laws, such as 0540 plus 23 and 0823 plus 26, but also Gaussian or log normal cases such as the others plotted here. And for 0540, just going one step further, this is a plot from data from Meerkat, where we've looked at this pulsar specifically. It's in the Large Magellanic Cloud. This pulsar is an emitter of giant pulses. Giant pulses have had. What I mean by giant pulses is that frequently this pulsar emits radio pulses that are much, much brighter than the mean radio pulse. Historically, this term has been used to describe pulsars that have pulses that are 10 times brighter than the mean. But in fact, the more physically meaningful definition, I think, is that there are pulsars with a power law spectrum of flux, where there are pulses that are 10, 100, or even 1,000 times brighter than the average pulse. And so this is just to show you some sort of typical phenomenology that you see across the population. On the shorter timescales, but not the extremely short, on the pulse-to-pulse, let's say, timescales, these observations capture the time dependence of the emission process on the timescale of the rotational period. And the variability you see here, which includes long nulls, but also changes from one state to another, and in some cases organized drifting of components. This is probably capturing the dynamic mechanisms in the pulsar magnetosphere, where the particles responsible for the radio emission, the timescales that they are being regenerated in the pulsar magnetosphere are of order the timescales that you see in the variability here. Then when you go to much longer timescales, and this is relatively new, this is sort of an emerging field over the last decade, pulsars show significant variability on timescales of months, years, and even decades. And what this plot shows is the shape of the pulse profile in blue in the top row here, compared to a constant, let's say, template in magenta, where you see that at this interval D, which corresponds to this line here on the timeline at the bottom, the pulsar grew a new component, which you can see in the residual between the observation and the template. And this component has persisted until today. In fact, we're producing a paper on this pulsar with data that goes all the way back to almost 1972 or 1970 when this was first discovered. What's the key point here? Pulsar timing that you hear about quite often relies on being able to cross-correlate a template of the pulse profile with the observed pulse profile, and the accuracy of measuring the TOA and the precision of the time of arrival depends on the pulse shape emitted by the pulsar being as constant as possible, or as close as possible to the template. If you start having changes in the pulse profile that are not matched by the template that you're trying to time it with, this introduces an error. And it has become apparent that these errors exist in the data, and we need to start understanding where they come from. Okay, so when people talk about the population of pulsars, they also always refer to something called the PP dot diagram. So this is the diagram that places pulsars in different positions depending on their period and their first temporal derivative of the period. This is what this looked like in 1988, which I think was the year that I first heard about pulsars in my life, and it was due to an episode of Carl Sagan's Cosmos, and he was interviewing Jocelyn Bell or something of that sort. In 1988, there were a few hundred pulsars known, and they all had pulse periods above 100 milliseconds or so, apart from a very small number of millisecond pulsars down here. And one of the objectives of pulsar surveys, pulsar searches, let's say, with current telescopes and with the SKA, is to fill out this space. So between 1988 and 2015, for example, the PP dot diagram changed significantly. And it has revealed a whole bunch of interesting subpopulations, as, for example, the young high E dot and gamma ray emitting pulsars at the top left corner up here, with periods typically of sub 100 millisecond and relatively large P dots, large temporal derivatives. Then there's the bulk population of normal pulsars, which some people consider to be boring, but at the same time, there's so many of them that you're always bound to find interesting corner case examples in there. And for that reason, I find them particularly interesting, I have to say. There's the group of neutron star binaries. And in this group, we know of a single pulsar binary. So a neutron star binary where we observed both sources as a pulsar was detected about 20 years ago. And the population of millisecond pulsars, which are recycled. So the pulsars that have been recycled by accretion from a companion, and they also have high E dot, so high rotational kinetic energy derivative. And they're also gamma ray emitters. So that's quite interesting. The red points here and the red points here are gamma ray emitters. And it's worth noting this, because I'm going to talk about that in a bit. There's another little population up in the top right corner there, which are the inferred high magnetic field pulsars. And I'll talk to you about how that inference is made. And these are the pulsars that were formerly known as anomalous X-ray pulsars or soft gamma repeaters. So do the pulsars in the PP dot diagram, are they different populations that originate through different channels and different mechanisms, or do they evolve into each other? This is a very important question, because we have to understand what the birth rates are, especially if there's a relatively solid connection between neutron stars and core collapse supernovae, and we think we understand the rate of those in our galaxy. So can we do the numbers agree in terms of the observed neutron star population and the supernova? So there's a bunch of model-dependent parameters that are also very, very important in pulsar astrophysics, and I highlighted them in the red box here, and they refer basically to the textbook canonical pulsar, which I've shown in the plot on the left. So the canonical pulsar is a little neutron star with a dipolar magnetic field, and the misaligned magnetic axis to the rotation axis gives rise to a force that pulls out charged particles from the surface of the neutron star. And these charged particles are accelerated in the magnetosphere because the field lines of the magnetic field extend beyond the so-called light cylinder. In other words, the radius of a cylinder where the co-rotation velocity becomes equal and greater to the speed of light. So these field lines can't close effectively, so they are they can accelerate. Particles can keep moving along these field lines, and particles are accelerated. So the textbook description of the radio emission process says that some sort of seed particles from the surface, or some more radical ideas include cosmic rays and so on, they're accelerated by a potential above the polar cap that's formed due to the misaligned axes. And this leads to radiation, which is in gamma rays initially. These photons annihilate and they produce electron-positron pairs, which are the secondary particles that are accelerated along the field lines and generate the radio emission. So assuming all of that, then you can infer the surface magnetic field of the pulsar. And the assumption from an observational point of view here is that the derivative of the period that you measure is entirely due to the fact that you have a gigantic spinning, strong dipole magnet. Okay, so under that assumption, you can actually say the magnetic field is this. So in this equation, you'll see there's the radius of the star, there's the inclination angle between the magnetic axis and the rotation axis, and there's also I, which is the moment of inertia. The moment of inertia is typically assumed to be something like 10 to the 45 grams centimeter squared. And that's what you would get if you assume 1.4 solar masses and a radius of 10 kilometers. So that will be ballpark correct for all neutron stars. The other inferred parameter is something called the characteristic age, which is nothing other than the period divided by 2 times the period derivative. The assumption there is that all pulsars are born with a very, very fast rotating period, and over time the period gets longer and longer because they are slowing down due to the breaking, because of the fact that they are a gigantic magnetic dipole that's misaligned. So apart from those two parameters, there's also E dot. So E dot is just the rotational kinetic energy that's being lost by the fact that the pulsar is slowing down. So irrespective of what is slowing the pulsar down, you can still measure or derive E dot by this combination of P and P dot. And you see the moment of inertia is in here as well. And it helps to try and parameterize the rotational frequency derivative in this way in order to construct a parameter called the breaking index, N, which is the spin frequency times the second derivative of the spin frequency over the first derivative squared. And I'll tell you about why this is an important quantity in a bit. And so there are, interestingly and worth mentioning, there are pulsars that are being discovered that have very slow periods now. There's an observational bias against finding these sources with surveys, so it's kind of hard to do for various reasons. But there are now pulsars that are quite a bit slower than the bulk of the population here, as you can see, ranging up to a few seconds, above 10 seconds. There's a pulsar now with a 76-second period, and there's another radio source that has a period of 18 minutes, although it's still slightly unclear about whether that's a neutron star or a white dwarf of some sort. Anyway, the point is that when you, despite the derived parameters that I highlighted in the red box, when you see PP dot diagrams in pulsar-related papers, they commonly come with these sets of diagonal lines. So you see diagonal lines that have constant characteristic age on them, and diagonal lines that have constant magnetic field or surface magnetic field strength. So the field strength going through the main bulk of the pulsars is about 10 to the 12 Gauss, the inferred surface magnetic field. And the characteristic ages go from a kiloyear here to 100 kiloyears to 10 megayears and so on. So these things are plotted typically in PV dot diagrams, despite the fact that there's a whole bunch of assumptions that need to be justified in order to do this. One way or another, pulsars are going to be evolving on the PV dot diagram, and if you just consider the fact that that those intervals in characteristic age are on a logarithmic scale, this part of the PP dot diagram will always correspond to the oldest, the population of pulsars that have been around for the longest period of time. And for that reason alone, you would expect that that's where the majority of pulsars sit. So in other words, there's 10 million years of interval between here and here, whereas there's only about 1,000 years somewhere here. So it's not possible in a plot like this, now that we have 3,000 odd pulsars, to show what the density of sources is at any given area of the PP dot diagram. But I think it's worth, from now on, plotting PP dot diagrams using density plots, so you can see actually where the majority of the sources lie. And they don't actually, there's no pile up of old sources here. It seems that the peak of the population lies actually in the middle of the distribution, and you can see the millisecond pulsars in the corner here. And so it's my own view that these lines of constant magnetic field strength that go like this line here, and this line here, and this line here, and the lines of characteristic age, which are these lines here, this one, this one, this one, are not, oh sorry, this one, this one, this one, are not as, well, they need to come along with their caveats and their assumptions, whereas the lines of constant E dot, which are the tilted ones, the red ones here, are less, require less justification, and they also explain some nice properties and some nice classifications of the population. So let's talk about the emission itself. Okay, so radio emission is coherent. If you take a bunch of pulsars and you measure their spectra, the typical thing an astrophysicist would do, you find that their spectra are steep negative in the radio. They have a peak that's somewhere around minus 1.4, minus 1.5. It has been reported in the past. In our most recent paper with data from the Meerkat radio telescope, we find that the mean actually is somewhere around minus 1.7 or 1.8. But you see there's an extremely broad distribution of the spectral index. So most pulse spectra you can fit with a power law of some sort. That's good. But there are frequency-dependent effects that are probably related both to the emission mechanism of the pulsar and to the interstellar medium that intervenes, that prevent you from, that broaden this distribution, let's say. And there's another effect as well, which is that broadband instruments, broadband radio telescopes, have a very different beam size at the top and bottom end of the band. And so positional uncertainties of the source itself might lead to further steepening of the measured spectral index. One way or another, they are relatively steep negative spectral index objects, but not always easy to distinguish from AGN just from their spectrum alone. So the radio emission process is coherent, and we understand that because we can attribute some sort of brightness temperature to it, and it turns out to be above 10 to the 20 Kelvin. So this is a typical plot that exists in the pulsars and transients community to show this sort of thing. So on the y-axis you have radioluminosity measured as the flux density times the distance squared, and on the x-axis you have a quantity that describes the temporal duration times the bandwidth. And this kind of plotting things in this way means that effective temperature, constant effective temperature lines can be plotted as diagonal lines on this plot. So you see, this is where pulsars lie. This is where fast radio bursts lie, assuming you use the distances that are inferred, and some other extraordinary objects are above this cutoff. So let's talk a little bit more about E dot then. So E dot is just the temporal derivative of the rotational kinetic energy, and it turns out you can derive it if you measure P and P dot, and it's given by this equation here. And the luminosity that we observe, as I said, is just we just usually measure it as the flux density times the distance squared. So if you take the observed luminosity of pulsars and you try and parameterize it as a function of P to some exponent small p and P dot to some exponent small q, which of the derived physical properties of the pulsar does the luminosity relate to, is the question. And so with the latest MeerKAT data, for example, we are able to do that. In the background here, the colors represent something called the Spearman p-value. Okay, so this is just the darker colors show you the values of A and B, which are the exponents of P and P dot, for which the luminosity matches best the observed population luminosity. And you see basically that, so I've got three lines plotted on here. The red line is the line that corresponds to the luminosity being some function of E dot. The blue line, the luminosity would be some function of characteristic age, and the dark blue line would be that the luminosity is some function of the surface magnetic field. And you see, in fact, that the p-value, the Spearman analysis shows you that it's much more likely that the radioluminosity is correlated to E dot. So E dot is the physical property that the radioluminosity correlates to, and that's not surprising because E dot tells you what the reservoir of energy is, and some of that turns into radio. So I'm going to talk to you briefly about the polarization geometry in B field. So pulsars are highly polarized, and the polarization means that you can say something about the geometry. So as the pulsar beam sweeps past the telescope, you see that the polarization angle executes a very smooth curve. And this is what you would expect to see if you're looking at the projected magnetic field lines from a gigantic dipole. And there's a very simple equation that describes that, where alpha is the inclination angle and zeta is the inclination angle plus the impact parameter. That's the shortest distance of the line of sight to the magnetic pole. And so I just want to show you some examples of what pulsars look like. Some pulsars are extremely highly polarized, almost 100% polarized, but then again, not at every rotational phase. Some pulsars show very complex profiles and only say a part of that expected S-shaped curve. So why is that? Some pulsars have very low degrees of, relatively low degrees of linear polarization, but possibly some circular polarization, and a distorted, wiggly position angle profile. And this is a case where the polarization is medium high, and the profile is also quite distorted, and you see very high degrees of circular polarization. So pulsars are sort of unique emitters of circular polarization. So why do we see such a variety of states? I mean, is there a way to reduce this complex parameter space, reduce the degrees of freedom? There's lots of questions here and some potential answers, but I just wanted to highlight these things for you. Can we generate an emission process, or can we envisage an emission process that generates all sorts of degrees of polarization, including circular polarization, including organized position angle swings and disorganized position angle swings. And there are some key observables here, like orthogonal jumps in the position angle, the degree of circular polarization, the frequency dependence, and the E dot dependence. And of course, all of these things you can, with modern telescopes, interrogate as a function of frequency. So the parameters that you associate with geometry, in principle, they shouldn't be related. There shouldn't be a frequency dependence. So observing a frequency dependence, as you see here, so these waterfall plots, the axis here is always frequency, and they're showing you the total power and circular polarization as well as the position angle. The fact that there is a frequency dependence tells you that there is a non-geometrical component to the polarization, which, if your aim is to understand the geometry, then you need to understand this. And if your aim is to understand how many pulsars there are, then you need to understand the geometry, because you need to understand how many of them are beaming towards you. So all of these things are always interconnected. I'll skip over this. The other simple observable quantities are the width of the pulse profile, so the width of the actual pulse. And under certain assumptions, you would expect the width to be a function of the pulse period. If the emission height above the star is constant, then the width you would expect to be proportional to the period to the -1/2. And depending on how you do your analysis, you might say that's the case, but in fact, the published results show a dependence on P as P to the -0.3. So that means that the emission height is not constant, most likely, as the pulsar evolves. And other things that we know about the population is that the degree of linear polarization is the highest for pulsars with the highest E dot. So the highest E dot pulsars are the youngest pulsars in the top left-hand corner of the PP dot diagram. And as the E dot value decreases, then the linear polarization also decreases. So again, coming back to those equations, what can we say about the strength of the magnetic field as pulsars age? Well, it's getting to the point now where we've observed a few pulsars for over 40 years, and the breaking index that I mentioned earlier is a diagnostic as to whether the primary mechanism for spinning down pulsars is magnetic dipole breaking. So for the Crab pulsar, we can see that the breaking index over time has wobbled up and down with a significant departure here, but somewhere around 2.5 something. And if magnetic dipole breaking is the only, is the dominant mechanism for spinning down, then this value of the breaking index should be 3. So for the best pulsar we have, we know that this value isn't 3. And there was a paper by Marcus Lower et al. In 2021 that published breaking indices for, I don't know, 20, 30, 40 pulsars, I don't know how many there are, that showed that there's a significant number of pulsars where the breaking index can be measured not to be 3. So that casts some doubt, or some further doubt, to the value of these surface magnetic field measurements and characteristic age measurements. I should also say that some pulsars seem to have glitches. So that glitches are sudden spin-ups of the pulsar that are followed by a recovery to the original period or thereabouts. And if you account for these spin-ups, then over a long period of time, they also seem to be spinning down with a breaking index of somewhere around 3. So in other words, the short-term spin or spin down properties of pulsars may be determined by something to do with the intrinsic properties or the coupling of the superfluids in the interiors of neutron stars to the crust, but over long periods of time, pulsars may be spinning down according to magnetic dipole radiation predictions. I think I should speed up, so I'm gonna skip a couple of these things and just talk a little bit about the connections between the radio beam and the pulsar spin down. So I've spoken a little bit about the changes in the pulse shape, and one of the key developments there, which I'll show in this plot here, over the last decade, was not only that the pulse shape changes, but that the pulse shape sometimes correlates with dramatic timing events. So you see, when this pulse component appeared in this pulsar in 2005, the first derivative of the pulsar spin also changed by 15% over a period of 100 days or so. And in fact, it showed a very dramatic changing profile for 3 years before it stabilized at a value that's 15% different to what it was before. This coincided with a change in the pulse profile. But the interesting thing here is that if you relate these numbers to characteristic ages and magnetic fields and so on, they imply a very, a jump in those values, which is clearly not physical. So there's clearly another mechanism at play here in terms of how pulsars spin down with time. So why do we need to find all the pulsars? Well, currently there are very, very small populations of the most interesting objects. So there's one double pulsar and there's a small number of binary neutron stars. So it's unlikely that we can find examples in there where we can easily measure the things that we're interested in measuring. We want to find sources like hierarchical triples, and I'll give you an example of that, to measure or to test general relativity, and other relativistic binaries for the same purpose and for measuring masses very well. And we want to find rotationally stable millisecond pulsars in order to conduct the experiments of the pulsar gravitational wave detectors, which I'll talk to you about very briefly now, actually. So when you hear about pulsar SKA talks, you hear about the pulsar timing arrays, and these rely on having a group of very stable millisecond pulsars in the timing sense, distributed around the sky, where you can measure correlated variations in their timing history as gravitational waves, very low frequency, nanohertz frequency gravitational waves cross these arms of this galactic scale gravitational wave detector. So this relies on having a few tens of millisecond pulsars with extremely high timing precision. And at the moment, the number of pulsars that we can do this with is limited to maybe 5. So we need to increase the millisecond pulsar population by a factor of 10 in order to find the 50 that are needed for this experiment. And this experiment will probe the in-spiral phase of supermassive black holes at the center of galaxies. I talked a bit about hierarchical triples, and this is, the dual case of this, where you have a pulsar orbiting a white dwarf, a young hot white dwarf, and the two of them are being orbited by a cool old white dwarf. And in this system, you can actually test the equivalence principle in GR, because you have a pulsar falling in the gravitational potential of a white dwarf, and you have another white dwarf falling in the gravitational potential of the white dwarf. So you can test whether these two things behave in the same way. So the gravity doesn't depend on the form of the concentration of mass. And it's really interesting just to leave you with the high precision of pulsar measurements. This is really interesting how you derive these properties from these kinds of systems. These are the timing residuals from the radio pulsar in that system, assuming that it's stationary as an isolated neutron star somewhere up in the galaxy with a given period, the period at which it was discovered. And of course, you see that the residuals, so the model assumes that the period the observed period is constant, but of course, the residual shows you that the sinusoidal residual shows you that the apparent period is changing in a sinusoidal way, as you would expect by a pulsar orbiting a binary companion. Now, all of the data shown here in these little color dots have error bars on them, so you can get an idea of how well these things are measured. If you look inside that zoomed region, you see those little dots, which are the measurements of the radio pulse times of arrival, the residuals actually, and you see that the residuals actually fall on another sinusoidal curve with a much shorter period, which is the signature of the second orbit of the orbit around its own companion. So once you derive all the Keplerian parameters of the triple system, the residuals of the timing model drop down to the microsecond level, as you can see. So that's how you can do this kind of measurement, and how you can then address things like the equivalence principle in GR. So what does the SKA actually what are the stated goals of the SKA science project for pulsars? Well, we want to triple the current known pulsar population, and in doing so find all these interesting systems, including the highly relativistic systems that can be used to improve tests of gravity in the strong field regime by at least 1 order of magnitude. And we want to also find at least one pulsar black hole binary, which will allow really interesting GR tests and have some consequences on quantum gravity. Please don't ask me anything about that. We want to detect gravitational waves, of course, and that involves increasing the number of millisecond pulsars by an order of magnitude, such that we have these stable sources, timing sources, distributed around the sky for nanohertz frequency gravitational waves. And we want to improve the mass-radius relation, so the equation of state for neutron stars, by more than an order of magnitude by finding these sources. And the SKA is the optimal instrument to do this, and it all boils down to those 4 points. It has large instantaneous sensitivity. It has a large field of view which can be covered with multiple beams, with a large number of beams, to search for and time multiple pulsars simultaneously. It has a large frequency bandwidth, so you can correctly or as well as possible account for frequency-dependent effects and probe the astrophysics of the emission mechanism and the interstellar medium. And it has accurate polarimetry, which gives you a lot of information about the details of the radio emission and the geometry of neutron stars. So that's all I have to say, and I hope this wasn't too technical. I know it's a lot of information, but I think it's useful to have this slightly more in-depth view of how pulsar astrophysics works these days and why we're interested in these large instruments in the future. So thanks very much.
Thank you very much, Aris. So now the talk is open for questions. Teresa, who invited Aris to give this talk, will manage it. So Teresa, your talk.
Thank you. So yeah, I just wanted to say first of all that we are so happy that we did invite you, because that was an absolutely excellent colloquium, super interesting and very pedagogical. And my own research is very far from pulsar research, so I'm a good test group for this. And it was pedagogical while not being too lightweight at the same time. And it was clear that you enjoy talking about these topics. So I really enjoyed that. Just wanted to express that.
Thank you.
And I have a couple of questions myself, but I'm going to see first. I see there's already a few here. Ruben Lopez Cotto, do you want to start up?
Yeah, sure. So thank you very much, Aris, for the nice talk. I have a question regarding the pulsar timing arrays that you mentioned. So you said that there are only 5 millisecond pulsars that can be used there, but from the paper from the nanograph collaboration, I think they used several more, right? So maybe what is this discrepancy? Are they using some non optimal MSPs or something like that?
I'm being a bit controversial, and I'm also aware of the fact that this is all recorded and so on. But
okay, I'm just asking out of curiosity.
That's fine. That's fine. I think the point is, if you want pulsars with timing residual, this is the metric by which a pulsar is being assessed as a good or bad timer for the pulsar timing array is the RMS of the residual of the, after you've got the timing model, you get some residuals compared to your data and the RMS of these residuals. So if you want these residual, the RMS of the residual to be on the tens of nanoseconds scale, or 100 nanoseconds, which is the kind of thing that you really want for the measurements of the stochastic gravitational wave background. And for that, you also need multiple sources that you can cross-correlate to get the signature of the gravitational wave, which affects pairs of lines of sight simultaneously, let's say. So for that, you need sub 100 nanosecond, or thereabouts, timing residuals in RMS. And if you look at the whichever pulsar timing array publications there are these days, there are of order, I'm going to say 5 again, not to be too critical, but of order 5 sources that achieve that. Of course, what you do, I mean, if you're carrying out this program, you are timing millisecond pulsars and trying to improve your timing models to get the lowest possible residuals for any pulsar that you can. And there's a lot of effort going into minimizing these residuals with more clever techniques. For example, time and frequency variable pulse profiles that better, match as a template, match the observed profile itself. So there is work on reducing those timing residuals for all these pulsars, but at the moment, the number of millisecond pulsars that satisfy the criteria for this experiment is very small. Let's just say very small. And so the surest way to guarantee success for this is to increase the known population by a factor of 10. There's nothing.
But how is this gonna improve by one order of magnitude with whenever SKA comes? Are we gonna get the timing residuals better for already known pulsars, that already known MSPs that are out there? Or are you talking about new MSPs that will be coming, for which we will be able to measure better the timing residuals?
I'm talking primarily about the second, but I hope that also to some extent the first. Okay. But you are raising a very good point, because of course there is a certain amount of time that needs to pass in order to have a timing baseline to detect nanohertz gravitational wave. So if you find new sources which are very good timers, they will only become, they will only become appropriate for this kind of experiment after 40 years, right? But that's still okay. That's not really a problem. It just means that things happen further down the line, but it still means it's possible. So both of these things I expect will happen. Increasing the population will mean that you find more pulsars that are rotationally stable, which is really what you need, the most sort of conservative thing that you need.
Okay, thank you very much.
Thank you. I'm trying to see if there's any more questions here, or maybe I can take the chance to ask one of mine. So I was intrigued by earlier in your talk, you talked about how the pulsar shapes can change with time. And you said there was one particular one that you have data from the 70s onwards. Mm-hmm. Mm-hmm. And so when I look at a galaxy, for instance, if I have data from the 70s, there is just very limited information I can get out of that. So I was kind of wondering, how reliable and comparable are these old observations compared to the new ones?
It depends what you're looking for, is the answer.
Right.
It just happens that, you know, this is the source I was talking about. So this has data from 1989 onwards, but I have a plot. I was tempted to put it in, but we're about to submit this paper, and you know, I thought I'll leave it for the next opportunity. We have data from the 1970s from this pulsar. This pulsar happens to have such a big change that the you know, the changes in the time resolution of the recording instruments or of the sensitivity and so on don't really, you know, they're not sufficient to smear it out. You can see the profile, the characteristics of the profile at this level all the way back to the earliest dates.
Okay.
I think this is an atypical example because the changes here are, you know, of the order 100 sigma compared to current estimates of some sort of uncertainty. But I think, yeah, it's atypical in the sense that the older data are from, so the telescopes we're using, you know, Parkes, Effelsberg, these telescopes were all built in the 70s, so that the sensitivity in terms of collecting area has been there all the time. What has changed is the ability to record data at a very fast rate, so we don't have the time resolution. The bandwidth of the original receivers and backends was also very limited compared to now, so we don't have the frequency coverage as well. So in general, I think your situation also applies. That it's difficult to use the very old data sets to infer something new.
Right.
But in very rare circumstances where the changes are very dramatic, the old data sets are very, very useful.
Okay, that's really cool. It's unusual that you can have such use of the data for that long time, as you can in this case.
That's right, yeah.
Are there any more questions here? Otherwise, I might ask another one. You don't mind?
No, at all. No.
So this is you were one of the co-chairs for the Pulsars science working group for the SKAO. So this question is kind of related to that, and this is something I've been wondering a while. I assume there may be some overlap between the Pulsar science working group and the transients ones, at least in potential commensal use of data. And so I was wondering if you could just talk, mention a little bit what overlap and what differences there would be in particular for use of data. And this is maybe a very wide question, so you don't have to be exhaustive, but just a few examples, because I've been wondering a bit about why isn't this an enormous big group together, for instance. Then I realize as I'm listening to your talk that Pulsars is maybe a little bit more specified that would warrant to have its own group. Well,
that's right. So yes, I noticed that in your original email, and I sort of thought about that a little bit. So you know, the field of pulsars has been around for a long time, and we know quite a lot of things about the astrophysics of pulsars, as I tried to highlight today. And so we know quite specifically what we are after in terms of what the telescope capabilities have to be in order to find them, in order to use them properly to extract all the science. In the case of the transients working group, it's phenomenology driven, right? It's not source driven. So they're interested in finding things that are variable on shortish timescales. And what that thing is not important. So, well, it's important, but it doesn't drive the program. And so I think there's a few things to say that are a bit more concrete. So one of the things I work on is the pulsar backend for the SK, and the pulsar backend is the same backend as the one that detects fast radio bursts or fast radio transients. And so there's no distinction there. That's the that will find things that are variable on short timescales in the same way that it finds single pulses from pulsars, etc. The transient science working group, I think, has and science cases that are currently operating on telescopes like Meerkat and so on, has done very well to illustrate the synergy between timing and imaging, right? And this is something that pulsar astronomy has traditionally not done, but I think it will do more of it in the future. So the transient science working group is, I would say, more focused on the imaging side of things and borrows techniques in the time domain from pulsar astronomy. So that's kind of the, that's the quick summary. I'd also like to say that we're organizing a meeting this summer in Greece, in fact, it happens, with the title Timing and Imaging of Compact Sources with, SK and SK Pathfinders, which brings together these communities, both in terms of the science and the methodologies. And, one thing to say that, maybe a little bit provocative, a little bit controversial, is that a lot of the sources that the transients, the transients community find, I think, are going to be explained as emission of some sort from neutron stars, whether it's regular pulsars or magnetars or some other form of a neutron star. So yes, there is a lot of overlap there, but I think there's a distinction in the techniques mostly, and in the fact that there are no very clearly defined questions like the ones that the pulsar community has.
Okay, thank you so much. I just realized we are a little bit over time here, and apologies for hogging the time in questions, but I don't see any more questions. If you have any, please speak up. And otherwise, we might linger a little bit online afterwards too, right, René?
Yes, okay. Yes, we can stop the talk here, stop recording, and we can stay a bit if Aris can stay there, of course.
Sure.
So thank you very much for this wonderful talk, and I hope everybody enjoys this colloquium. Thank you.
Thank you.